Do you sometimes go an entire day without thinking about calculus? If so, shame on you. You should be taking this seriously. It's important and it's a lot of fun. All right, so here we go with some ideas from uh, the last chapter, the sequences and series, diving right into power series, which I will never forget. I was told this when I was in graduate school from a guy who's a professor now at Iowa State. He's a math professor. When he was an undergraduate, he said to me, if you want to open a can of whoop ass on a problem, use power series. And I didn't know what he meant, but now I understand. It actually is a powerful tool. It can be used in a lot of clever ways. But anyway, let's see what power series looks like. Remember, we had 1/2 plus 1/4 plus 1/8 plus 1/16 dot 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 adds up to 1. First thing we ever did in this chapter. Now, if I throw an x to a power on top, because remember this is 2 to the first, 2 to the second. So what if I have x to the first, x to the second, x to the third, all the way up to x to the end, over 2 to the n? This should converge if x equals 1, because we just did that. And it certainly converges for x equals 0, because you're just adding up a bunch of zeros. A bunch of zeros adds up to 0. So I've got these values that it works for. Does it work for like x at 1/2 or 7/8, or what about like -1/3 for x? So the idea is what usually happens with a power series. So power series just means you have x to a power and some kind of coefficient, usually in the denominator. That's what a power series is. It's just a sum for series of x to powers. That's all. So where does this thing converge? What values of x? Because here's what we know so far. It converges for 1, doesn't converge for 2. You can see it fails for 2, because if I have 2 over 2, that's 1, and then 4 over 4, that's 1. But if you add up an infinite number of 1s, it adds up to infinity. So it fails for x equals 2. So it works for x equals 1. It works for 0. Does it work in here? Does it work in here? Does it work over here? What about for negative numbers? So there's a test, and it's called the ratio test. It's really the hardest working test in rock and roll. The chapter that we're ending with has a bunch of tests. The ratio test is the king. The ratio test works great on so many things. The other tests are nice. They're kind of situational. It's sort of like having a game. Like if you want to get into it, I'd be glad to. Like the comparison test is interesting because you compare a series that you know converges to a series you're not sure if it converges. And if you can come up with some little math trick to be able to compare them term by term, you can get an answer. But it still doesn't give you what it converges to. It just gives you that the series converges. There are people who love that stuff, that can do it all day. I actually kind of like it too. It's not something that I would do all day though. But this thing, ratio test, is a very big deal. Here's the ratio test itself. The series, a power series, is a sub n x to the n. A sub n is the name of the coefficient. It's all the stuff that's not x. So for you actually just check the series. You can even put in fact put the x's in. The x to the n things in here. Put them in there too, because that's where they go. So you check what you do is you take the n plus first term and divide it by the nth term. And it's almost always fractions. So you have a fraction divided by a fraction. Well, you guys know what to do with a fraction divided by a fraction. You flip and multiply. So we have the n plus first term of our questionable series here, divided by the nth term. And we're going to take the limit as n goes to infinity. And we need this limit to be less than 1. That's what the ratio test is. Well, everybody, when you flip and multiply, everybody cancels except for a single x and a single 2. And it's an absolute value. And there's a reason for that. So you have x, for this limit to be less than 1, x has to be less than 2 or above -2, because remember the absolute value of -2 is still 2. So this is called, this guy right here is called your radius of convergence. That's your interval of convergence. The radius of convergence is 2. The center of the radius of, or the center of the interval of convergence is 0. So you got to be able to do a ratio test. It's an important idea. Going to use it a few times. Let's step up to another problem. So just another problem here. You can probably see the answer coming from a mile away if you understood what we just did. I'm going to try and find where does this converge. Well, this 5 down there is a big clue because, I mean, just look at it. If x equals 5, you're adding up an infinite series of 1s. So it can't be x equals 5. But x equals 0 works, x equals 1 works, x equals 2 works. Those would all be geometric series. If you put in a constant for x, the geometric series, you can actually find what the sum converges to. You could find the total sum. All right, so what's the radius of convergence? You can see the answer is going to be 5, but let's do it here. It's going to be x to the n plus 1 over 5 to the n plus 1, and I'm going to do the pro move. This is times 5 to the n over x to the n. Because the ratio test, remember, it's the n plus 1th divided by the nth, and you want this to be less than 1. And everybody cancels except for a single 5 to the first power. Everybody cancels except for a single x to the first power. So for x over 5 to be less than 1, x has to be between, but not including, negative 5 to 5, because of the absolute value. Now the question is, why do we have absolute value? Why can't we just leave the absolute value off? Because we'd still get the 5, wouldn't we? But we want a thing called absolute convergence. This is a very important idea. The math people are extremely proud of this idea. If you fool around with your calculator, you can either program it to do this or you can just do it yourself. You do a half minus a third plus a fourth minus a fifth plus a sixth. This thing converges because it never gets above, it never goes over 0.5. You know, it waffles, but it seems to be converging to a number, but it's not a famous number. It's not an easy number to see, but it's got to converge because the values stay positive and they stay close to 0.5, but it never goes over it. You can think of it like this. You start out with a block of stone, and you took away a part of it, and then you added a smaller part of it, and then you took away a smaller part of it, and then you added a smaller part, and then you took away a smaller part, and you added a smaller part. You never get back to the full block of stone. You never get back to a half is the big idea. But we already saw that if you put all plus signs on that same sum, it diverges. So we care about the plus or minuses because you can have a convergent series if you allow it to alternate, but the same series diverges. So the book calls this series here conditionally convergent. It converges if you leave the minus signs on. But if you change them all to plus signs, it diverges. It turns out, and this is very big, it turns out that only absolutely convergent series can be manipulated. Manipulated mathematically. Move terms around, or take derivatives if it's power series, or even integrate term by term. You must have absolute convergence, and the ratio test is the test for absolute convergence. So if you have absolute convergence, for a power series, that means you can take derivatives, you can do all sorts of stuff to it. You can treat it like a function of x. Very big idea. And here's another big idea about it, is because now that also solves these kind of problems. Because when people are studying math, they look at things like this: 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1, dot, dot, dot. And they used to worry about this kind of thing because the concept is pretty easy, and yet the sum cannot be found. And the math people for maybe 100 years wondered, why is this kind of animal such a bad thing? And it's because you can see it's not absolutely convergent. If you made them all plus signs, it would just be adding a series of ones, which goes to infinity. So you can't do that. And it also gets you out of the hassle of, hey, if we shove a couple of plus ones to the front, we still have enough minus ones to cancel out the rest of the minus ones. So maybe this sums up to 7. Or 6, you get whatever you want. Just shove some extra ones up front and let everybody else cancel out. Well, that's no way to do math. You'd like to know precisely what this thing is, and it turns out that no, this is a math expression that is poorly worded. It's not a good idea. It's not a clear math idea. It's not absolutely convergent, so you can't talk about it as if it's a number. It's not a number. So it's nice to have that kind of category. The math people are extremely proud of that. Now with absolute convergence, though, we have a whole family of extremely powerful moves, and it is this. It's Taylor series, ladies and gentlemen. Taylor series. And this is what we'll be focusing on. I've got some really good ideas. So Taylor series says this. F of x is equal to the sum from n equals 0 to infinity of f upper n of little a x minus little a to the n over n factorial. Let's meet the family. You should know n factorial. 1 factorial is 1, 0 factorial is 1, 2 factorial is 2, 3 factorial is where it starts getting interesting, because 3 factorial stands for 3 times 2 times 1. 3 factorial is 6. 4 factorial would be 24 then, because you have to multiply this by 4. So the factorials grow really fast. You have a button for this on your calculator. This guy here is a funny notation. F upper n stands for the nth derivative. So this is an amazing formula. You can write a function, as long as you can take derivatives of it, you can write a function in terms of its lower derivatives, which is really weird. F upper 0, which would be the first one, is the same as f of x, because you're not taking a derivative. F upper 1, we never wrote it that way because it's just f prime. But you can see that upper is handy for when you're taking the 10th derivative. Who wants to write 10 primes? Now, who's little a? Little a is just a number. It's just a real number. It could be any number. Little a is just a number. And what it is, now look at this. Look at this series here. If you let x equal to a, if you let x equal to a, just look at this formula and see what happens if you let x equal a. That says, okay, x equals a, this side would be f of a. Now, over here, let's see what we get for x equals a. For x equals a, you get the 0th derivative, which is the original, evaluated at a, times x minus a minus a, to the 0 power. This guy turns out to be worth a 1. And then, remember, 0 factorial is a 1 as well. So I get an f of a plus. Now look at the rest of the road. I'm going to take the derivative of f of x, that's f prime of little a, whatever that turns out to be, times a minus a to the first. This 0 survives. So I get a 0 times f prime of a. It literally doesn't matter what f prime of a is. And for the rest of the terms, this factor is going to be 0 for the rest of its life. You get a bunch of zeros over there. So f of a equals f of a. Isn't that cool? Now, that means that this series converges at x equals a. And if you remember what happened on the previous screens, that means that there might be an interval around it where it converges, and that would be the radius of convergence. How would you find the radius of convergence? Ratio test. That's it. So let's see some famous Taylor series. All right, quick terminology. Taylor series, you can use any number for little a. But if you have little a equals 0, it's called a Maclaurin series, because at the time, so this was 20, 30, 40 years after Newton, mathematicians were busily playing around with the problems and the ideas. And there was a Scot named Maclaurin who studied exclusively the a equals 0 case on his own. He didn't steal it from, the guy's name was Brooke Taylor. He didn't steal the idea from Brooke Taylor. He was working on it on his own. Taylor has the more robust thing because he has it for any number little a. So, but Maclaurin does, we still use his name once in a while. Oh, I did a Maclaurin series. You say it like that. So let's everybody say it together. I did a Maclaurin series. We do the Maclaurin series a lot because little a equals 0 is very handy. So here's e to the x. Now you guys know all the derivatives of e to the x are e to the x. So the 7th term, the 7th derivative, I'm sorry, is just e to the x. Now if we do a equals 0 for this Taylor series, an amazing thing happens. So let's do this thing. Okay, so this is going to be equal to the 0th derivative, which is that with that, and then it's x minus 0 to the 0 over 1 plus e to the 0 x minus 0 to the first over 1 plus e to the 0 x to the second over 2 plus e to the 0 x to the third over 3 factorial, which is 6, plus dot, dot, dot. I think we can simplify this. I see a pattern here. I've got a, let's see, I should be getting, for this thing, I should be getting a 1 plus x plus x squared over 2 plus x cubed over 3 factorial plus, I can do the nth term, x to the n over n factorial. And this guy is equal to e to the x, for God's sake. Are you kidding me? This is an extremely deep idea. You guys all have one of these things, I presume. Remember, you have this thing called a calculator. How does this calculator do e to the x? How does it do it? Because if you know a little bit about computers, you know that it's very easy to add and subtract. Multiplication is repeated addition. It can do that. Exponents is repeated multiplication. It can do that. But how does it handle something like e to the x? Does it actually have a little chip that lets you look up values or something? No, no, no. Because it can only do certain operations. It does only simple operations. For e to the x, it could do a Taylor series. It could have wired in this series because it's a polynomial. You can get a chip to do a polynomial easy. So the Taylor series was one of the things that was in place for hundreds of years. And when people conceptualized the idea of a calculator, they said, hey, we could make a scientific calculator with all the famous buttons, just write them the things as Taylor series. We don't have to come up with some bizarre command for exponents. You know, we could just use this kind of stuff. Anyway, so that's a powerful thing. Now let's do another one. We're going to do 2 more. 2 more will be on the next video.